Okay, this is another session in a video lesson in General Physics 2. Shout out again for my students, grade 12. Good luck on your National Achievement Test. Okay, for this video lesson, we're gonna cover some problems involving magnetic fields and forces due to magnetic fields and the motion of charges and current in carrying wires in contexts such as but not limited to determining the strength of the Earth's magnetic field, mass spectrometers and solenoids, and the concept of magnetic flux also. Okay, before we move on to at least one of the problem solving examples, let's just have a brief review of our key concepts. So for the magnetic field, it's B or beta, a region around a magnetic field or a moving electric charge within which the force of magnetism acts. So the unit is Tesla. For the magnetic flux, it's phi. It's the Greek letter phi. It's not theta, it's phi. The measure of the amount of magnetic field passing through a given surface area. So its SI unit is Weber. Faraday's law of electromagnetic induction. So connected to induction course. This law states that changing magnetic fields can induce electric current in a coil, such as solenoids. The induced electromotive force in a coil is proportional to the rate of change of magnetic flux through the coil. Then we have the Ampere's circuital law. It states that the magnetic field in space around an electric current is proportional to the electric current which serves as its source. And the Lorentz force. The force exerted on a charged particle moving through a magnetic and electric field. The force is given by F force is equal to Q, the charge, E for the electric field plus B velocity times B or the magnetic field. Okay, let's now have your sample problem involving magnetic flux. The problem is a square loop of side 10 centimeters is placed in a uniform magnetic field of 0.5 Tesla. The magnetic field is perpendicular to the plane of the loop. Calculate the magnetic flux through the loop. So just like what we are doing in normal classroom, usually we begin with what are the given. So we have the area, 10 centimeters, which can be converted into 0.1 meters. And to get the area, we just have to square one side of the square, right? 0.1 meter squares, it's 0.01 square meters. For us to be able to get magnetic flux or pi, beta times the area times the cosine theta, which is, if it's perpendicular to the plane of the loop, it's 0. The final answer would be 0.25 Weber. So in your notebook, I'd like you to compute for the magnetic flux if the theta or the angle is 45 degrees. Okay? And the same given. Okay, we are now on the last part of our video lesson. Just like in our previous video lessons, don't forget to post your reflections on the comment section. And at the same time, as a bonus part of this mini lesson, my question is, what do you call the Greek letter used for magnetic flux? Then combine it with the unit for magnetic flux, and lastly, combine it with the year that you can see here in this slide. Then use only small letters. With this, you would be able to access the Google file for the Physics 2 reviewer. Okay, that's the end of our lesson. Always remember, sa PIQ'S TV, panalo ang natuto.